So for this section, we are going to learn about the regression equation, and we're going to talk about the R value, which is the strength of the correlation. Now, there's a lot to unpack when we get to the linear regression t-test that's going to kind of unlock everything for us in this chapter here. So let's get started by just doing some basics to talk about R, because the numerical value to the strength of the correlation is going to be the letter R. So sometimes you'll see uppercase letter R, sometimes you'll see lowercase letter r, but either way, the R value is called the correlation coefficient. So if you're reading a textbook or you're reading most online homework, they're going to ask for the correlation coefficient, and they're talking about the R value. Okay, so that is important to know. So it is important that you can guess the correlation. If a scatter plot looks like a sneeze, then the R value is close. Probably should spell it right. Close to 0. So if you see just a bunch of random dots, but they're not random because they were actually collected from data, on your X and Y axis here, here's your X, here's your Y, then this is going to be close to 0. If the scatter plot looks closer to a straight line going up, then the R value is closer to 1. So, for example, if you have dots that kind of fall in a pattern that goes from low to high, this would be closer to 1, but if you have dots that are very straight, this line is much closer to 1 than this. This might be a 0.6 or a 0.75, and this might be a 0.95 or a 0.98. So the same thing goes down if the scatter plot looks closer to a straight line going down. Then the R value is closer to -1. So here's where things get a little tricky, because you can have dots that move down like so, and again this would be probably -0.65 or -0.70 or -0.8. But then if they really kind of fall in line here, according to a straight line, then this is going to be something like -0.95 or -0.97. You see, this right here is the continuum of the possibilities for our R value. So right over here, this 1, if the lines are perfectly straight, there's not a single dot out of line, it would be a 1, a perfect correlation. So usually over here, between some indeterminate amount that we don't know until we actually bust out our test value, our critical values and our tables, there's this shaded zone somewhere on the right hand side to tell the difference between a strong positive correlation and a weak positive correlation. So strong positive and weak positive is kind of determined by this shaded zone here. And we're going to be figuring out what the shaded zone actually is as we do problems in the next section. Now, of course, there's a symmetrically balanced shaded zone on the left-hand side to tell the difference between the strong negative from the weak negative. So your R value can be between -1 and 1. If it's really close to -1 or 1, it's considered a strong correlation, just like these pictures here. These are strong correlations because the dots follow a straight line. Now, we get into a little gray area with these pictures because although there is a trend, maybe the dots are not close enough to the line to actually show strong versus weak. And that's where we're going to be really diving into this in the next section. This section, however, is just all about getting the values, getting the things onto the calculator, and starting to try to analyze what they all mean. Now this shaded part, which I'm shading in purple here, this shaded part is called the critical region. Critical region. And if you land there, you will reject the null hypothesis. Now, it's kind of abrupt to talk about the null hypothesis, but let's just do it for a moment and we'll tackle it more in depth in the next section. The null hypothesis is somebody who's crossing their arms and saying, no, there's no correlation. So the null hypothesis is right here at this spot right here in the middle of all this weakness. The null hypothesis is saying there's no correlation. You shouldn't be looking at these two variables. But if your results land here in the shaded zone, then you can say, well, we're definitely witnessing a rare event. And this event is so rare, we have to question whether, we should even look at this null hypothesis. Because the null hypothesis says there's no correlation, but obviously there is. It's strong positive or it's strong negative. So that is really the goal. When we get all the way through the next section and all the examples I give you, we are going to be looking at correlation. We're going to be testing to see whether that correlation is strong enough for us to abandon the idea that there is no correlation. So we'll be doing that with hypothesis tests, but mostly we'll be doing it with the help of our graphing calculator, because what we're about to do is we're about to spend some time learning how to get the most critical part of your information that you'll need for this entire chapter on your calculator. So I just want to read this here because we will be spending a lot of time in the next section going over how to find that critical region section and where to plant the flag of your test value. Because if you plant your flag in the critical region, you reject. And if you plant your flag not in the critical region, in that giant white space along, in the weak side of things, then you're just going to say, okay, there's still no correlation. So let's revisit some older data and let our calculator find all this information for you. Now, it's possible that you still have this on your calculator. I, in fact, don't, because I made this video on a different day. So I'm just going to quickly type this in and then have it for the next critical step. Okay, so I typed in all that data. Now what I'm going to do is show you on the calculator how to get the information that you need that we're going to talk about on the next page. Well, in case you did need a reminder though, to get the data in the calculator, you hit the stat button, then you hit the enter button. To get to the statistics you have to enter, we're going to type our X into list 1, and we're going to type our Y into list 2. So here's where I would go to get your most important calculator function you're going to use this whole chapter. When you've typed in your data from list 1 and list 2, click Stat, click over to Tests. You can do so by clicking the right arrow twice, but of course you can also hit the left arrow once to get to Tests. Then I would scroll up, even though you're at the top of the menu, by scrolling up a few times. Okay, by scrolling up a few times, you can get to something called the LinRegTTest. The linear regression t-test. Linear regression is going to use a least squares means test to basically measure the distance, vertical distance away from the line of best fit, or the line that it's trying to fit to all the points. And it's trying to make the smallest squares possible. There are a couple cool videos and exercises to show you how to do this by hand, but we're going to let the technology do it because it will give us great results and it will allow us to get to the analysis faster without all the arithmetic. So the linear regression t-test looks something like this. You click the Stat button. You can move to the left or to the right to get to the Tests menu. But then again, I'm going to push up because this is almost at the bottom of the list here. See, as I push up on my calculator, it's option F, the linear regression t-test. And it's a t-test because we're not going to have a lot of data. Just simply put, we're just not going to have over 30 pieces of data. And also, the t-curves are nice because they do get adjusted based on the sample size of the problem. And we'll talk more about that important sample size. So click on the linear regression t-test, and then you're going to keep all of these defaults. Always do list 1, list 2. We're going to do 2 tail tests for the remainder of this course, although you can maybe find some rare examples of you having to go less than or greater than, but we're going to choose 2 tail for all of my examples. But be aware that, you may want to read carefully in case they ask for those. And we're not going to type in the regression equation and plug that into a variable. We're just going to go to calculate every single time. So just bypass the screen, or if your calculator is really old and doesn't give you that screen, just hit enter. And then here we go. Look at all of this information, and you might say to yourself, I'm a bit overwhelmed. Well, click the down arrow key. There's more from there, okay? So you can click up and click down and notice all of this information. Alright, so what I'm going to do on the next page is break down what all of this is used for. And that will end this video, and then we're just going to spend the videos and after this using this and putting it into cool applications, okay? So let's break down what all of this means. So this is going to be this important values from the LinRegTTest. This is going to be kind of your owner's manual for all of this information. Now, first of all, this is the format of the slope and y-intercept equation. Note that in this format, slope is b and is after the y-intercept. Okay, which means that for this course going forward, this y equals mx plus b, no, we're not going to use that format. We're not going to put the slope before the y-intercept. We're going to use this format. Now, if your online homework asks you for this y equals mx plus b format, be flexible, okay? Just be flexible. Like this is how it's written on the calculator. This is how the homework may want to use it. Just please look very carefully at the format of the problem, and you may want to try one versus the other, and then reach out to me if there's any discrepancies. Of course, I will always look over tests to make sure that you did the right thing. It's just that XYZ homework or some other online homework modality didn't quite read it correctly. Okay, so what does this mean where it says beta not equal to 0 and rho not equal to 0? Now, first of all, you are probably expecting me to say P, but that actually is the Greek letter rho, R-H-O, as in row, row, row your boat. Now, what this means is this is going to be our alternative hypothesis. So our null hypothesis is, whoops, let me put a nice looking H sub 0 there. Our null hypothesis is going to be rho equals 0. And rho, think of it this way. Rho is the Greek letter R, okay? And this Greek letter R, that looks like the letter P, that means that there is no correlation, rho equals 0. So our alternative is always going to be rho not equal to 0. So for the rest of this chapter on the work that I assign, rho is equal to 0 and rho is not equal to 0. That's your null and alternative hypothesis. Isn't that awesome? Now you have your null and alternative hypothesis for every single problem I ask on my paper pencil stuff and my tests. So this is cool. So again, we don't need to worry about beta. That's an application we're not going to concern ourselves about, but just this output of rho not equal to 0, hey, that's our that's what we're going to be using here. Now the t, this is the test value, and we have seen these test values before when we did t-tests back in the previous unit, that unit that we did all those hypothesis tests. So the test value is also on the t-curves, which we're going to make look like normal curves because we're not artists. Okay, curves. These test values are on t-curves, and we're going to mark them there, and we're going to have a flag where the t-curve is. I had a student put a little flag at the top of there, and I was like, yeah, let's put the flag on top. Yeah, so that's what the t-value stands for. And then, of course, the p, this is the p-value, or the percent value. Now, these p-values here are really important because the p-values get compared to alpha, and alpha is always going to be 0.05. I'm not going to use any other alpha for the rest of this unit. Your book may stray from it every once in a great while, but for the most part, it's going to stick with 0.05. So your test value is something we're going to use, and the p-values are something we're going to use. Now, degrees of freedom. Now, you knew what DF stood for because you've been in this course for months now, and you've seen this in hypothesis testing, and you just saw it in our chi-squared unit. But in this case, the degrees of freedom is n minus 2. n minus 2. And the best and simple way I can kind of explain, and I'm going to do so quickly here without actually getting into the minutia, we have two different variables, x and y. So that's why it's n minus 2. Now, that might not be the grad level explanation here, but that's really kind of all you would need to know, that if you have an x and a y, this is n minus 2. Now, you might be thinking to yourself, well, back in the hypothesis test chapter, didn't we have two variables? And we didn't. We had actually two groups with the same variable. And even the before and after was one group with the same variable. So in this case, we have two, x and y, where in previous cases we had samples, or two different groups with the same variable. So that's why it's n minus 2. So just be aware that your calculator is going to spit this out. So the degrees of freedom for the whole course is n minus 1, except for correlation problems, where it's n minus 2. Now, A is the y-intercept, and that shouldn't be too big of a stretch, but write it first. Okay, unless your homework your digital or online homework wants it second, but again, this is going to be our standard. B is the slope, and the slope is the number in front of the intercept, in front of the x variable. And important here, so note, if b is negative, use subtraction. And that's really a helpful thing, because the b value is either going to be positive or negative. It's positive, use addition. If it's negative, use subtraction. Also appropriate is y equals a plus negative b. You can also add a negative as well. So you can use, for positive correlation, y equals a plus bx. And if you have negative correlation, y equals a minus bx or plus negative bx. Again, if you're typing things into XYZ homework or any other learning management system, you may have to play around a little bit before it says, oh yeah, that's what I was looking for, because it may not have both or all the different forms for the negative correlation. But you'll get used to that. And again, if you have trouble, let me know. So the S is one we're not going to use until the very end of the chapter. This is called the standard error of the estimate. And the standard error of the estimate, very simply put, is the standard deviation above and below the line. And again, we're going to get into this at the end of the chapter, so I don't want to spend any time on it. Now, these two can easily get confused. The more important value right now is R, which is the correlation coefficient. Okay, that is where we basically measure the strength between the x and the y variable. But the r squared, we're going to talk about this in the next video coming up. This is something called, and believe me, you're going to want to keep this worksheet in front of you to not get this confused with r. This is called the coefficient of determination. The coefficient of determination. This is the closest we're going to get to this dangerous word causation, but the coefficient of determination is going to be something where we can look at how y gets affected by x. And I want to really take my time on that one, because r squared is when people make pretty bad leaps of judgment, or they make poor analysis decisions, because the r value is very straightforward, very elementary, but man, the r squared, by taking this r value and multiplying it by itself, you can get into some real dangerous thinking. So we're going to take our time in the next several videos and break down why this r and r squared are different, how they're different, and how we can best use them without getting in trouble. But keep this in front of you, because we're going to have a lot to talk about in the next upcoming sections as we pull this all together, our small unit on correlations.